All right. In the past two videos, we've done a lot of work to hopefully give you a good idea of what is actually happening inside a circuit and why electrons would even want to move through the circuit to begin with. What we're now going to get into is a little bit of the fun, and that's the math behind the electricity. So in this video, we're going to cover the math in two topics. We're going to cover the math behind current, and then we're going to cover the math behind resistors, which is ultimately known as Ohm's law. Okay. In the last video, we covered current a little bit, but we never really talked about how you can calculate it. We just talked about what it is. If you remember, current was defined as the amount of coulombs of charge that is passing per unit of time. So as time goes on, how much charge is actually flowing through a particular point in a circuit. So if we mathematically look at that, current could be calculated by taking the change in charge, or in other words, how much charge is passing per unit of time. All right, now think about it. When electrons are moving through a wire, because that's what's powering the electric circuit, it's electrons. When electrons move through a wire, they're going to experience resistance based on quite a few factors, okay? And before we get into those factors, let me just kind of give you a visual about what I mean by resistance. Let's imagine your hallway at school. All right. Let's say classes were in session and I wanted you to go from one classroom to another. Would you experience a lot of resistance in the hallway? In other words, would you experience a lot of trouble getting from one room to the other, or would it be fairly simple? It should hopefully be very simple because there's not anybody in the hallways. Everyone's in class, so the hallways are really clear. You can get from one place to another very easily. However, if I were to ask you to go from one classroom to another during a passing period, that gets a little bit more difficult because now the hallways are crowded with other students. Not to mention, if I asked you to go through a hallway that was maybe narrow, or maybe the hallway was very long, etc. There's a lot of factors that would dictate how much energy or effort it took for you to go from one classroom to another. In the same way, it can be applied to a wire. So we find that there's four factors that will dictate the resistance that electrons feel as they are going through and conducting electricity through a wire. First of all, the actual conductivity of the wire itself, meaning the material. Some materials just conduct electricity better than others. For example, the best materials to conduct electricity are materials like gold or silver. Now, if you know anything about gold or silver, they're expensive, and so we typically don't make mass amounts of wires from gold and silver. It's just too expensive. And so a good efficient metal is copper. Copper is prevalent enough in nature to where we can produce it and it doesn't cost as much as doing gold or silver. However, there are circuits that are made of gold and silver. They're obviously very small because we don't want to use a lot, but we find that gold and silver materials are much better to produce electricity than copper. And that's because gold and silver will give up more electrons than copper does. But other than that, what's other factors that affect resistance? Number two, thinner wire has more resistance. That's like if you were trying to walk through a hallway that was thinner or narrower, it could potentially be harder for you to go from one place to another, especially if the hallways were crowded. Number three, the longer the wire, the more resistance. Same thing as before. If you're trying to get from one classroom to another, it takes more work for you to do that if the hallways are much longer, if your distance to go is much longer. So longer wires have more resistance. And that in an electron sense, that's because more collisions are going to happen as the electrons are moving throughout the wire because there's more atoms. And finally, we see that the higher temperature, the more resistance. And that's because when you increase the heat or increase the temperature, all the atoms that are inside the wire, and there's lots of them, there's like millions and millions, all of those atoms are actually going to move faster. Heat makes atoms move and vibrate faster. And if they're vibrating faster, that means there's going to be more collisions between all the little particles that are making up a wire. If there's more collisions, that means there's going to be more resistance for the electrons as they travel through. So those are the four factors that can cause resistance as electrons move through a circuit and through circuit elements. Now, resistance has the symbol R, and it is a measure of a material's resistance to flow. Okay, let's do some calculations. What I recommend is go ahead and pause the video and then hit play to reveal the answer. Okay, A current of 3.2 amps flows through a wire. How many electrons flow through it? We're going to look at our equation that we just saw in the previous slide. Current is equal to change in Q over change in T. Okay, so my current, my I, is 3.2 amps. And I want to know how much charge, or excuse me, how many electrons is going through each second. So for 1 second. So in 1 second, 1 times 3.2 is going to give me 3.2 coulombs of charge for every second. Now I know that there is 1.6 times 10 to the negative 19th coulombs for every 1 electron. So the coulombs cancels out, and my number of electrons is going to be found by taking 3.2 divided by 1.6 times 10 to the negative 19th, which gives me 2 times 10 to the 19th, which is answer A. All right, let's look at one more. A current of 80 milliamps is traveling through a wire. How many electrons pass through it in 10 minutes? So very similar like before. We know our current is 80 milliamps, but notice the milli. It needs to be changed to just regular amps. And so milli, there is 1,000 milliamps in 1 amp. Milli means 1,000. And so I'm going to move the decimal 1, 2, 3 spots to the left because milli is a smaller unit. And so 80 milliamps is the same thing as 0.08 amps. And that's equal to delta Q over the time. In this case, the time now is 10 minutes. My unit of time has to be in seconds in order for me to cancel it out with amps. And so 10 minutes times 60 seconds is going to give me 600 seconds for my time. If I take 600 times my 0.08 amps, that's going to give me 48 coulombs of charge is passing in that amount of time. And now here's where I convert my 1.6 times 10 to the negative 19th coulombs of charge for every 1 electron. Coulombs cancels out, and 48 divided by 1.6 times 10 to the negative 19th is going to give me my amount of electrons is 3 times 10 to the 20th. Okay, let's talk about resistors now. Resistors are also known as circuit elements or loads, but a resistor is used to reduce the voltage applied in a circuit. Because sometimes, depending on what the circuit element is, it can only operate at a certain voltage. If you have too much voltage or if you have too much current, it could not operate properly. And so resistors are in charge of controlling the amount of voltage that's applied in a circuit at a particular part. Now, a resistor in real life looks like this. They're these little tiny cylinders that have these metal probes that go out to the side. That's what a resistor looks like. The schematic view of a resistor is a jagged line that looks like this. Any circuit element, however, acts as a resistor. A light bulb could be a resistor. A button on a machine could be a resistor. Anything that is in a circuit that uses energy is going to be acting as a resistor because it's using the energy that's passing through. Now, resistance, remember, is the measure of the resistance to flow, and it's measured in the unit of ohms, which looks like a horseshoe, but it's actually the Greek symbol omega. Now, Ohm was a scientist, and Ohm came up with a very important law that we use in electricity. Ohm's law is actually right here in the center. This is the traditional view of it, which is voltage drop is equal to the current times the resistance. But we can actually rewrite that in 2 other ways. We can rewrite it in terms of solving for I. So current is equal to the voltage divided by resistance. Or we can write it in terms of solving for resistance, and that would be voltage divided by current. But all 3 of these are the same equation. They're just rewritten in different ways. So let's go ahead and get some practice with that. A light bulb with a resistance of 15 ohms is connected to a 12-volt battery. What would be the current in this particular circuit? Okay, so current is going to be found by taking my voltage divided by my resistance. In other words, 12 volts divided by 15 ohms. If I divide those two, 12 divided by 15, that's going to give me my answer of 0.8 amps, which is option B. A 2400 ohm resistor is connected to a 20-volt battery. Find the current in milliamps. So first thing we need to do is we just need to solve for amps. Okay, so we want to find the current again, so I'm going to use my I equals voltage over resistance. My voltage is a 20-volt battery, and the resistor is 2400 ohms. That's a lot of resistance. So 20 divided by 2400 gives me my amps as I'll write it down here, as 0.0083 amps. Now, it wants the answer in milliamps, so I know that there's 1,000 milliamps for 1 amp. So for every 1 amp, that's equal to 1,000 milliamps, or just moving the decimal place 3 places to the right. And that's going to give me 8.3 milliamps, which is option letter C. All right, find the voltage that will produce a current of 15 milliamps in a 1200 ohm resistor. So voltage is equal to I times R. And so voltage is equal to my current, which is 15 milliamps. Let's change that to amps. 3 places to the left. 1, 2, 3. So my amps is 0.015 n times my resistance, which is 1200 ohms. 1200 times 0.015 is going to give me my voltage of 18 volts. Okay, let's do one last practice because we did a lot of definitions, especially in the first 2 videos. So what we're going to do, let me scroll down here, is we have options A, B, and C. A is for current, B is for voltage, and C is for resistance. Let's go through and make sure we understand what each one is. Number 1, measured in amperes. That is going to be your current. Measured in ohms. That is going to be your resistance. A flow of charge. That is defined as the current. Depends on length and width of the wire. That is your resistance. The rate at which charge passes a given point. That is going to be current. Measured in volts. That is going to be B, your voltage. It describes the potential difference from one point to another. That is your voltage as well. Opposition to the flow of electric charge. Opposition, that's going to be resistance. This concludes the video on Ohm's law and current and resistors.